All right, welcome back. It's my pleasure to welcome Yuyi Zhong from the National University of Singapore. She's going to talk to us now about enhancing abstract refinement for neural network verification. Take it away.
Oh, thank you. I'm Yuyi from National University of Singapore, and I'm here to present our work, Arena, Enhancing Abstract Refinement for Neural Network Verification. So neural networks have been well investigated and applied to various real-world applications, including speech recognition, facial recognition, autonomous drive, and language translation. But it has been found that even well-trained neural networks can be vulnerable to adversarial examples. For example, we have an original input image X that is classified as panda by the network. Then we apply a small perturbation on top of this input and obtain a new image that still looks like a panda to human eyes, but the network now wrongly classify it as something else. And this constitutes an adversarial example that is human imperceptive but can fool the network to do wrong classification. And this is a very dangerous behavior. What if an autonomous car wrongly classifies a stop sign into a go sign? Then it could cause severe accident and damage. So therefore, it is important to provide safety guarantees of the networks, saying that unsafe status will not be reached within a certain perturbation size. So one example safety property could be robustness against our infinite norm attack. So the inputs of the infinite norm attack include an input image and a perturbation parameter epsilon. And given this attack, each pixel in the image, instead of taking one intensity value pi, can now take any value between pi minus epsilon to pi plus epsilon. Therefore, this attack returns us an adversarial region, which is the Cartesian product of pixel intervals. And the robustness property is defined as, for all images within this adversarial region, they will be classified the same as the original image. So for example, your input image is image A over here, and image B is within the adversarial region. But still, this image A and B, they should all be classified as label 1. There are many existing works to do robustness verification. For example, abstract interpretation-based tool like DeepPoly, which use a polyhedra, as shown in the diagram over here, to capture a set of concrete values a neuron could possibly take. However, abstract interpretation suffers from precision sacrifice as it introduces over-approximation error, and it's also and this knowledge is also included in the keynote talk just now. Therefore, there are works like DeepSRGR to refine the abstraction via existence of spurious counterexample. However, those current works fail to do verification when the property is violated and still have room for improvement of precision and efficiency. So therefore, we propose our system that conducts both falsification and verification while maintaining a certain level of efficiency. So in general, the inputs of our system include the network to be verified, the input image, and the perturbation epsilon. So we firstly send the inputs to the initial abstract interpretation process, and if succeed, we directly return verification. But if abstract interpretation fails, then we conduct counterexample guided abstract refinement, where this refinement process could return us either verification or falsification if adversarial examples are detected, or inconclusive if it times out. So the contribution of our system are listed as follows. So firstly, for efficiency concern, we can eliminate multiple adversarial labels at the same time to do successful verification. And to improve our verification precision, we deploy multi-relu convex abstraction. And also we can detect actual counterexample to falsify the safety property. We implement a prototypical analyzer named Arena on CPU and evaluate it with the state-of-the-art CPU or GPU-based analyzers. And the results show that we can achieve competitive precision and is scalable enough to handle network with up to 50K neurons. So the outline for the rest of the talk is given as follows. I will firstly give an illustrative example, and then I will give the general description of our system, followed by the evaluation results, and I will conclude this talk. So I will firstly describe about our verification process using this simple network. So given this network and the input intervals to be -1 to 1, we want to verify that the whole input space will be classified as label 1. To do so, we apply an initial abstract interpretation on this network, where the abstract domain is designed to contain 4 elements: linear lower constraint, linear upper constraint, concrete lower and upper bound. And for nonlinear ReLU function, as in diagram A over here, we will over-approximate its behavior with the upper constraint as in this blue line over here, and the lower constraint as the green line. To verify robustness, we need to prove that label 1 is dominant, meaning that Y1 must be greater than Y2 and Y3 at all times given the input space. But from the previous abstraction of the network, we can only obtain the subtraction to be -0.2, which fails the verification. Thus, we need to proceed further and prove that adversarial label 2 and 3 to be infeasible. And for the existing abstract refinement method DeepSRGR, it attempts to eliminate each adversarial label one by one, while our proposed method eliminates multiple adversarial labels concurrently. In here, we introduce a batch size delta, which is the number of adversarial labels to be eliminated in a batch. And in this running example, we can set this delta to be 2 and prune label 2 and 3 at the same time. So in order to eliminate both label 2 and 3 together, we try to refine the network abstraction via linear programming. So firstly, the constraint set of LP solving will include the linear constraints of all neurons, where we name it as the network encoding pi, plus a disjunction over here. And please note that this constraint set actually encodes the existence of adversarial examples that with one classification label 2 or 3. And the objective function of LP solver will be set to either minimize or maximize input or unstable ReLU neurons given the constraint set. And finally, LP solver returns tighter bounds of the neurons, leading to a better abstraction, where this tighter abstraction can show the existence of adversarial examples to be spurious, meaning that it doesn't actually exist. However, the technical issue is that we have disjunction in our constraint set, where linear programming does not naturally support the disjunction of linear inequalities. And to address the challenge, we will use conjunction of linear constraints to over-approximate this disjunction. So in more detail, we compute the over-approximate convex hull P of the disjunction under network encoding pipe. And because a convex hull is represented as a set of linear inequalities, linear programming will be amenable to handle pi conjunct with P. And we will leverage double description method to compute such a convex hull. So I will now briefly describe about double description method. So in general, there are two ways to represent a convex polytope. The H representation that takes the intersection of closed half spaces, where each half space is a linear inequality. So for example, a 3D cube can be represented by 6 surfaces, where each surface is a linear constraint. Or we can choose to represent it using V representation that takes a set of external points. For example, a cube can also be defined by 8 vertices. And double description method is to maintain both H and V representation. So this duplication could be beneficial because to compute the intersection of 2 polytopes in H representation is easy, as we only need to take the union set of linear constraints. On the other hand, to compute the union of 2 polytopes is trivial in V representation, as we take the union set of the vertices. And lastly, V representation and H representation can be transformed to each other. And we leverage those features to compute the over-approximate convex hull. So in detail, we firstly get the initial convex polytope associated with Y1, Y2, and Y3 under the network encoding, which is a 3D cube pictured in A, and each Yi is in its concrete intervals. And the convex polytope for the constraint Y1 minus Y2 is smaller and equal to 0 under this network encoding correspond to the shaping B, where this additional constraint is another cutting plane on top of polytope A. And given this polytope B, we also obtain the vertices of this polytope as well. And likewise, the second constraint projects to polytope in C. We also record the vertices of polytope C. And then we take the union set of vertices in B and C as the vertices of D. And from this vertex representation, we transform into H representation. And now the convex hull P is represented as the conjunction of 7 linear constraints. So now our constraint set is fully conjunct and can be handled by LP solver. So we send the constraint set to LP solver and resolve input or unstable ReLU intervals. And the new bounds are colored in red over here. And based on the new intervals, the abstract values of other neurons are updated as well. And we color them in blue. So we can see that the abstraction of ReLU neurons are indeed refined from the original blue triangle to this smaller red triangle. And given the previous refined abstraction, we can now compute that Y1 minus Y2 or Y3 is greater than 0.2, making label 2 and 3 to be infeasible. Therefore, label 1 is dominant, and we successfully verified the robustness. In this one example, we successfully verified the property with a single round of refinement. But in general, our system conducts iterative refinement process. So in each iteration, we take the encoding of multiple adversarial labels together with the current network abstraction as our constraint set. So if this constraint set is infeasible, then we eliminate delta adversarial labels at the same time. And eliminating all adversarial labels results in property verification, as we show in the previous example. But if this constraint set is feasible, we send it to LP solver and resolve neuron bonds and obtain a refined abstraction, where this refined abstraction is used in the constraint set for the next iteration. So we will repeat this process until we have infeasibility or until we time out or exceed iteration threshold, which is set to be 5 by default. Then we return inconclusive. So in general, our system Arena has 3 features. So firstly, we have multiple adversarial label elimination, where we encode delta adversarial labels in our LP solver and resolve tighter bounds. And tighter abstraction leads to infeasibility of adversarial labels, as we show in the wrong example. Next, ReLU neurons are usually encoded independently, but we adopt multi-ReLU abstraction, capturing dependencies among ReLU neurons in the same layer, making our network abstraction more precise. And finally, as a feasible constraint set indicates the possibility of a property violation, we check if the optimal solution returned from the LP solver constitutes an adversarial example, so that we can do falsification as well. So we evaluate our system for robustness verification task, where we set a 2-hour timeout for each image. Otherwise, we consider the result as inconclusive. For the benchmark, we set our testing images as the first 100 images in MNIST or Cephalton test set. And we compare with 4 tools, including 3 CPU-based incomplete methods, where DeepPoly is the state-of-the-art abstract interpretation-based method, and DeepSRGR refines the abstraction from DeepPoly. And PRIMA improves DeepPoly by capturing dependencies among ReLU neurons in the same layer. And we also compare with one GPU-based complete tool, AlphaBetaCron, the best tool in competition. And finally, we present our parameter study of the batch size delta for multiple adversarial label elimination. So here we showed our testing networks, where we choose a wide range of networks with various numbers of layers and neurons, and the network with the maximum size has up to 50K neurons. And we choose a challenge epsilon for each of the network that is difficult to do verification and falsification. And we apply robustness analysis on candidate images only, where candidate images refer to those testing images that can be correctly classified by the network before perturbation. So we firstly show partial of the visualized results, where we compare with 3 incomplete tours on CPU. As Arena, DeepSRGR, and PRIMA all improve over DeepPoly, so DeepPoly is our baseline verifier, as colored in the blue bar over here. And for those images failed to be verified by DeepPoly, each algorithm will call up the respective refinement process to proceed further. And the number of verified images via refinement process is colored in green. And the falsification is colored in red. The yellow one means inconclusive. So we can see that Arena has more verification and falsification. And statistically speaking, Arena returns 15.8% more conclusive images than DeepSRGR, and 60.6% more conclusive images than PRIMA on average, with comparable or even less execution time than that of DeepSRGR. And for more experiments and time details, please check out paper. So we also compare with GPU-based tool, AlphaBetaCron, which is the winning tool of verification of neural networks competition 2021 and 22. So AlphaBetaCron is a complete tool based on branch and bound. The idea behind is to divide the original verification problem into subproblems by splitting neuron intervals. And this method is theoretically complete as we can split all unstable value neurons, resulting in subproblems without nonlinearity. So the splitting generates easier subproblems, and those subproblems can be solved by efficient incomplete verification methods. And verification of all subproblems means successful verification of the original problem. And we compare with the latest version of AlphaBetaCron. So the results are shown as follows, where Arena runs on CPU and AlphaBetaCron runs on GPU. So we know that Arena can verify or falsify around 80% images of that of AlphaBetaCron on average for the upper 7 subject tests. But for the last 4 test networks, AlphaBetaCron additionally introduced MI encoding to capture exact value functionality, and thus further improve the number of verified images. And the execution time of Arena is not competitive, since Arena used the costly LP solver Groby on CPU. However, the solving process can be implemented on GPU, which would result in a significant acceleration in the future. And finally, we present our parameter study of batch size delta. So eliminating delta adversarial labels at the same time requires the union of delta polytopes, which introduce imprecision. So therefore, we evaluate how batch size affects precision and efficiency. So here we present the number of verified images through refinement process and the average execution time per refined image from delta equals to 1 to delta equals to 5. And the study result shows that having larger delta can still maintain comparable precision while requires less execution time. So to conclude this talk, we propose Arena, which is an enhanced abstract refinement process where we can eliminate multiple adversarial labels at the same time to do successful verification. And we can also conduct counterexample detection to falsify the safety properties. And from the evaluation results, we can achieve competitive precision compared to CPU-based incomplete tools. And our tool is scalable enough to handle networks with up to 50K neurons. And we also compare with complete tool AlphaBetaCron and achieve close precision. So that's the end of my talk. I'm happy to take questions. Thank you.
Questions? Maybe I'll get started with a question. So you are able to do falsification, meaning you can present images that would confuse neural networks. Yes. Have you found any kind of new problematic networks that weren't discovered before with your tool?
What do you mean?
So have you using your tool, have you found some neural network that is not robust, that wasn't known before? Have you reported this? What was your experience?
So for falsification, Okay, so the falsification is with respect to a specific network, a specific input space. So if given this input space, we find one adversarial example with another classification label, then we return this adversarial example to the user, and that's the falsification. So even though, for example, given this the same epsilon, and for this input image, the network have adversarial examples for this input image, but perhaps for another input image, it doesn't contain the adversarial example.
Right. So I guess in the adversarial examples that you do derive, are they interesting and useful for the designers of the networks and for people consuming them?
Yeah, I think so. I think that's one of our applications, because the adversarial examples that we have is a concrete image. So we have the concrete image as the return adversarial example. So if the trainer included in their training data set, so we expect the trained networks will be more robust because it sees more adversarial examples than before.
Gotcha. And do they still satisfy the initial specification, which is humans can't really distinguish between the classifiers, but the machine does?
Yeah, because the perturbation is still a small perturbation that's imperceptible to human eyes.
Very cool.
Thank you.
Other questions?
So you have applied, thanks for the talk. It was a great talk. So you have applied your technique for the L infinity norm. Do you have considered other norms? I think you like L2 or some others that might exist.
I'm sorry, I couldn't really hear you very clearly.
Like the adversarial examples are defined with respect to a distance, which is measured in a norm. And so in the first slide, you restricted to L infinity norm, okay, because it's pretty usual to do that. But there are other norms that can be used to measure the distance between adversarial examples. So have you considered others?
I'm sorry, I could only hear the keywords like L infinite norm attack, but for the other parts, I kind of missed that.
Maybe
Can you perhaps rephrase?
Tell me if it's wrong. I guess it's asking, do you try to use another norm?
Attacking method?
No, distance measurements to measure the distance. Yeah, the measurements that you are right now using norm.
Right. So far, we are targeting on L infinite norm attack only.
And have you considered use different norm to measure?
So for other perturbation, for example, geometric perturbation, or for example, L2 or L1 attack, as long as after the attacking, the input space can be represented as the Cartesian product of concrete intervals, then our tool can still handle that. Yeah. Thank you for the question.
So did you test only against publicly available models, or did you train your own neural networks?
Oh, these networks are obtained from the trained networks by the others.
Okay.
Yeah.
Did you find any examples of networks that were trained on adversarial examples?
Oh, we do have. I think we do have networks with adversarial defense, like DeepSRGR. Yeah, we have 2 networks include that.
Cool, thanks for the talk. So I noticed that, so you do multi-neuron abstraction and polytope double description method,
yes,
right? Which is pretty similar to what PRIMA does. You outcompete PRIMA in a couple instances. Can you highlight sort of what the differences are in your method from PRIMA? and where you're sort of getting this performance gap?
Oh, because so basically, so you can understand this tool as, so PRIMA is like the convex barrier breaking, that kind of methodologies that consider multi-values. And so basically on top of that, we also include iterative refinement as well. So that's why we have additional precision improvements on top of PRIMA, because we have iterative refinement.
Thank you.
Thank you.